Hi, welcome back to the part 2 of Cadence common source resistive drain configuration of our MOS. So this is what we have done in the part 1, where we calculate how to set up the required DC bias point by testing or by calculating the appropriate width W and calculate the appropriate resistance value. And last time we also do the simulation in order to check the result of our drain current and also the drain voltage. And in this video we will do the simulation to check the way that we calculate the low frequency gain that we discussed in the part 2 of the small signal analysis of our common source resistive drain circuit. One small information: sometimes we can say that is the resistive drain because the resistor is connected to the drain of the MOS, or we can say this is resistive load. Now let's check the way that we calculate our low frequency circuit gain. In short, I would just say low frequency gain. To check it, I also put the equation over here, the equation that we discussed in the previous video over here. If you have not checked the part 1 and part 2, please check it, because this video is only the simulation of those previous videos. Okay, now I put the calculation here. To check it, first we need to prop out the GM, because in the formula we need GM and resistor, the resistor value, and the resistor value is here, and the GM is the GM of our MOS, the transconductance of our MOS. How to get it? We can press on our calculator. By the way, in order to get it done, first you need to run the simulation. At least you need to run the simulation once, so we can collect the data like this. And after we already collected the data of the circuit, we can use the calculator, and then we can choose OP, operating point, and we select the instance, which is our MOS in this case, because we want to prop out the GM, and we can find GM is here. And this term will appear in the calculator. If you don't know how to use the calculator, please refer to my previous video, which I also put in this video description. I talk about how to use calculator or use some expression in the calculator, expression in simulation. They are very important. Now we can export it to our McGraw file. I will do it very quick because I already set them, I already introduced them in the previous video. If you want to check it out, please check it out in my video description. Okay, now we have the GM, we can name it GM, and here's ID, we can name them, so when we simulate and run the result, it will be easier to see. Actually, we don't need to run our simulation again, because all of the data related to our MOS within our circuit is already simulated and collected or saved in the software, so we can just re-evaluate the term by clicking into here, and we will see that we got the GM, this value. Now we will calculate the gain in dB with our formula, and after that we will do the simulation and compare with the expression that we determined previously. But now we will use the expression to calculate the low frequency gain of a circuit. Next, we need to get the resistor value, and the resistor value is only like 12 kilo ohm. We can easily do that using the calculator. And we got the GM, we just need to jam times with 12 kilo ohm. So I use the scientific notation. E plus 3 means 12 times 10 to the power of 3. 10 to the power of 3 is kilo. Is 1000, means 12 kilo ohm. And according to our expression, we need to calculate this term in dB. How to do that? We go to this fn function. We open the function panel and we choose all, and we can type db, like we search for db20, and here we are. Double click and the expression will be included. This expression, to make sure that it will work, even though yes, we can see that our GM is positive, so for sure the expression in the calculator over here will be positive, so the whole expression will be valid. However, to make it sure that it will be positive, we can click on Fn again, functional panel, and we search for, let's choose all, and we search for absolute operator. Now we got the absolute operator, but it's enclosed the wrong thing that we like. Either you search for it, if you remember it, you can just type it like this. Okay, I think it's gonna be good. Before we export it, we can check whether our expression is good or not by click here. If we see the result, it means it's fine. The expression works correctly. Now let's go back and export the expression to our McGraw file. After export, we can go to Output Setup tab and check. Here we can see our expression. We can name it AVO, low frequency. AVO, or we can just say like A. Sometimes it's used as a symbol for gain, voltage gain. A, low frequency. And now we can save it. We go to results and we reevaluate, and here we got the gain at low frequency 18.52 according to the expression that I put here. Now we will do one more calculation, but with that calculation expression we can extract the value of the gain from the simulation itself, not from the expression calculation. So that's how we can check. We will extract that value from our model rather than calculation expression. And in order to do so, we need to have the AC analysis, because the gain relates to transfer function, and the gain at low frequency, it means we need to have a frequency sweep to get the transfer function, and then we get the value at the low frequency. So we need the AC analysis. The start time, it should be as low frequency as possible, because we want to see the gain at low frequency. So we put it 0.01, or you can just like 0.1 is fine. And the stop, we can put it as big as we want. Let's say I will say 1 gigahertz, 0.1 hertz to 1 gigahertz, and I click OK. After I set up the AC analysis here, you can like check or uncheck in order to determine which simulation you want to run. I check both of them, so it means when I run the simulation, both of the analysis will be run, and I prefer that way. So I can now go back to my other perspective of the McGraw file, and then I will use the calculator. What do I do here? First, I will need to get the VF, mean the AC expression. So expression for AC voltage. You can even see expression for AC voltage very much relevant to the transfer function. If you want to know why it's relevant to the transfer function, please refer to my previous video about low pass filter and cadence. When I do the analysis of a low pass in AC analysis or transient analysis, it will give you the idea why the AC voltage of a signal is relevant or is related to the transfer function. And then this will be our transfer function. However, what do we need? We need to get the gain in dB at low frequency. So first we need to convert the signal into dB. We choose functional panel and we do the same. we search for dB20, double click. We just use one term. I maybe double click too much, maybe just one click but not double click. One click and the term will enclose our signal. And next we need to get the value of our signal at low frequency. So we can again, we already opened the functional panel, we can choose search for value function, and then you click on it and you can see the signal is this one. Interpolate at, it means at which value on the x-axis that you want to get the value of our signal. So our signal is the transfer function on the y-axis, and on the x-axis is the frequency. And plot or print against time, no, because we are printing the transfer function is in frequency. So in frequency we choose circle. We click OK. And then we can evaluate it here. Expression evaluates to new because we have not run the AC analysis, so we cannot check our expression in that way. We just need at this moment export it to our McGraw file. So we export it to our McGraw file. We can say gain burst simulation. And in order to do the AC analysis, here we don't have any small signal in our circuit, so we cannot run the AC analysis. Or if we are able to run, we will obtain nothing. You can run it and you will see. We obtain here, we can right click and plot, we see nothing. Magnitude is 0. It means our simulation, AC simulation, is wrong. So we need to close it and we need to fix this problem. Is that we need to put a small signal input. And for common source configuration of the MOS, we have the input, small signal input at the gate, and the small signal output at the drain, which is our V out here. We don't have the input, so we need to have the input here. We can just delete this wire, and then we choose create by pressing the shortcut I keyboard on your keyboard, and we search for leaf library, analog leaf, yes, and we search for vSyn. vSyn means the source to generate our sinusoidal signal, and we connect it. And we will adjust the AC magnitude to 1. Okay, now we save our circuit. Warning, we can see the warning from here. Warning is here. Floating net V out, which is totally okay, because it's only a wire that I put in order to prop out the output signal. We go back to our McGraw file, we run, and then we wait. Now you can see we right click and we plot our drain voltage. You can see this is our transfer function. This one is not, this is the result from the DC response or the DC analysis, because we run two analyses at the same time, AC and DC. DC is not our interest, so we can close it. And here you can see this is our transfer function in dB. But this one is the magnitude in volt. It's not in dB, but the transfer function is plot not in dB. This is not plotting in dB. We can go back to the McGraw file and we can see. Okay, we can use calculator, and then we will plot this one in dB. We'll plot this is the signal in dB. Press plot. Yeah. So this is in dB and this is in magnitude. They are the same. You can see this is in volt, but this one is in dB, and they are the same. So if you want to read the value in volt, you can read it here. If you want to read it in dB, we will read it here, but we prefer to read in dB in this case. So the value, we can press V to have the vertical marker, and at low frequency, you can see at very low frequency, very low one. So that's why we call it low frequency gain. We got the value in dB is 17.65 dB. Equivalent in volt is 7.6 volt if we have 1 volt AC input at the gate. And now we go back to our McGraw file. This is our McGraw file, and you can see this is our low frequency gain when we calculated according to the expression that we deduced. But for this one is the low frequency gain that we extracted directly from our simulation. They are not too different. So we can say the expression or the way that we calculate is acceptable in this case. If you accept the error of the calculations not too big, so yeah, you can see they are very close, only 1 dB different. Maybe, yeah, only around roughly like 1 dB different. So we can say the expression that we deduced in the previous video when we introduced about the theory, how to analyze, how to do the small signal analysis of the gain at low frequency, somehow acceptable. So that's the end of the video. Thank you so much for watching, and if you feel the video is helpful, please give me a like or subscribe, and see you in the next video. If you find any wrong information, also leave me a comment. Thank you so much. Goodbye.